Start recording here. We're going to be talking about numbering systems here, and specifically we're going to talk about the base 10 system, which is the decimal system, which we've always used, and the binary system, but we're just kind of discuss the systems in general. So let's discuss the base 10 system. Now, we've been using this all our lives, okay? And, so basically you consider, well, if you've got 10 fingers, then you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then, well, when you, but actually the decimal system is truly defined because it has 10 unique symbols, okay? So the fact that it's the decimal system means that we have 10 unique symbols. And so 1 0 is 2 of those symbols combined. So the 10 unique symbols are 0. We don't normally think of 0 as being one of those symbols, but it is, and it's actually maybe one of the most important ones. Okay? And so when we take something like the number 505, okay, we could actually express that as 505 with a subscript of 10 to indicate that this is the decimal 505, as opposed to a octal or hexadecimal or some other base. Okay. All right, so when we look at large numbers, then we basically have to break these down. So you have like the ones column, and then you have the tens column, and then you have the hundreds column, and thousands column, and so on, right? So if you think about like scientific notation, you may have like some value like 7.32 times 10 to the minus 5 or something along that nature. And so we have this this value here. So now, the thing is that computers, digital computers, which of course PLCs are digital computers, and these computers do not actually have, or they don't actually have a way of adding or subtracting or really dealing with binary number or with decimal numbers. Okay, so computers don't really understand decimal numbers. They're binary computers, which means that they either have a 1 or a 0, and technically inside of that computer it's a voltage. So we kind of talked about that with the TTL logic voltage, 0 to 5 volts. Remember, with TTL, if you have between 2 to 5 volts, that's considered a high or a 1, and if you're below 0.8 volts, it's considered a 0. So the way digital computers work, including PLCs, because they are digital computers, is the fact that they can only deal with a high voltage or low voltage, which we like to describe as a numbering system with 2 symbols, 0 or 1. So the binary numbering system just has 2 particular values, either a 0 or a 1, which again inside of the PLC indicates it's either a high voltage or a low voltage for 0. So this is just kind of an example of like a transmission. If we were transmitting between 2 PLCs or a PLC and a PC, and we're transmitting data, we're going to send that data as a bunch of zeros and ones. All right, so when we talk about numbering systems, okay, for computers, in the automation world, we usually deal with about 4 different types of numbering systems. Okay, as I said before, the PLCs or computers, they really only use one numbering system, and that's the binary numbering system. The other numbering systems that we see here, base 2 is the binary, but base 8, base 10, and base 16, the computer can display values in any of those, but it's really only using truly the binary numbering system. And then at the bottom here, we kind of have binary coded decimal. Binary coded decimal is not really a different numbering system. It's just a encoding of a numbering system. So we'll look at that here at the end of the slides. But it's very important to understand how these different numbering systems work, how we can convert between them, and why we need them. Why do we use octal or hexadecimal? Okay, if the PLC only uses binary, and as humans we're most comfortable with decimal, why do we work with octal or hexadecimal? All right. So first of all, when you're talking about different numbering systems, you have to be conscious of the base that you're working in. All right. So here we have 123 base 10, or 173 base 8, or 001111011 base 2. Okay. Now, to understand these numbers, we have to understand what the base is, because if you don't have that base, you really don't know what the number means. Okay? And so this subscript gives us the base. Okay? When we talk about hexadecimal, hexadecimal has 16 symbols. And since decimal only has 10, which are 0 through 9, how are we going to symbolize 6 more symbols? And so what they've chosen to do was to use the first 6 letters of the alphabet. So A, B, C, D, E, and F are considered symbols when you're talking about hexadecimal. All right, so let's look at how do we convert between decimal to binary, or binary to decimal. So let's kind of start off here with a number. So if I had a number here like this, where we had just some number, okay, we break it down into its columns. So let me get a paint here open. I really prefer doing this on the whiteboard, but it doesn't display very well for you. So all right, so this over here, of course, is the ones column. And this is the tens column. And this is the hundreds. Okay. So why is that? Well, if we look, right, we have 10 to the second power is 100. All right. So if we have a digit in here, so if we have this digit in here, in this third position, that would be hundreds. And if we have one over in the last position, of course, that would be like the ones. So like if I had a number, let's say I have the number 324. So if we can place that in there, okay. So we have 3 times 100, and 2 times 20, or times 10, which would be 20, and then 4 times 1. So this would end up giving us 3 times 100 plus 2 times 10 plus 4 times 1, right, which of course then would result in 324. Okay, so when we normally don't think about that, when we see the number 324, we just, okay, well, that's 324. But in reality, what we're doing is this. We're taking this 3 times 100 plus 2 times 10 plus 4 times 1. So if you keep that in mind, when you go to a binary, so if you look at the binary case here, you kind of do the same thing, but instead of doing base 10, we're doing base 2. All right, so let me just check the chat here. Okay, I was just checking to see if there were any questions or anything. Don't see anything right now. So all right, so if we look at this now, we have here, we've got, 2 to the 0 is the ones column. So we still have a ones column. Then we have 2 to the first, which is a twos column. 2 squared, which is the fours column. And 2 cubed, which is the eights column, and so on. All right. So when you look at this, you see that each column here, we have the ones column, twos column, fours, eights, 16s, 32s, and 64s. Okay. Which with the with base 10, we would have ones, tens, 100s, thousands, and so on. But with base 2, we have the ones. You're always going to have a ones column. And then, depending on what your base is, you're going to have the next base. So if we wanted to convert the number 324, this is how we would do it. So we're going to take the number 324. Okay. And what we want to do is you actually want to start from the left-hand side here. Okay. So you take this one here, which is 128. All right. And so what I'm going to do is I'm going to divide 324 by 128. And so when we do that, we're basically saying, can the number 128 go into 324? And the answer is yes. How many times? Twice. Okay, so we can put 128 will go into 324 at least 2 times. It's actually more than 2 times. All right. So what does that mean? It means I did not take out my number, because remember, when binary, this is binary, we're doing base 2 or binary. And base 2 or binary, the only values that I'm allowed to use is either a 1 or a 0. Okay? The number 2 or 3 or 4, these are invalid. I can't use a 2 or 3 or 4. But what I'm saying here is like, hey, I took the number 324, which was the one I did on the previous slide, right? In the decimal, I was allowed to use a 3 or a 2 or a 4. But in binary, I'm not allowed to use a 2, 3, or 4, or 5, or anything else. I'm only allowed a 1 or a 0. And so when I take the number 324, and I'm looking here to see, can I take the number 324 divide it by 128. Well, the answer is yes, but I can actually do that 2 times. So what I have to do here is come over here, and I'm going to have to add at least one more of these. Okay, so I'm going to have to add one more of these, so we're going to have 2 to the 8th. Okay, so we're going to have 2 to the 8th here. So you already got a 2 to the 7th. So now I need a 2 to the 8th power, which is 256. Okay. All right, so now that I got 256, okay, then I'm going to start with that one. Okay, so I'm going to take 324, which was my decimal number. Okay, so this is 324 base 10. So 324 base 10. But what I want to do is see how many times can it go into 256. Okay, so I divide it by 256, and I'm going to get the answer then, of course, is it'll go into 256 once with a remainder. I'm going to shrink the font down a little bit here so I have a little bit more room. Okay, so I'm going to divide 324 by 256. And I can do that once with a remainder okay, so what's my remainder? I'm going to cheat here. $324 is 68. So I have a remainder of 68. Okay. All right, so that puts me a 1. So that's going to give me a 1 right here in the 256 column. So now I have a remainder of 68. So I'm going to take this remainder of 68 and I'm going to divide 68 by 128. And the answer is, can I do that and still have a positive value? Well, we can't do that. You know, 68 divided by 128 gives you a fraction. So I cannot do that and have a number greater than or equal to 0. Okay. So, you know, so if you take like 68 minus 128, okay, that's going to give you a negative number. Okay. That's going to give you a negative result. Okay. And so we can't have a negative result. So that's going to give us a 0 for the 128 field. So then I'm going to take 68, okay, because I didn't change that. I still got 68 remaining. I'm going to subtract 64. Now that I can do, right? I can do that. So I can subtract that once, and then I'm going to have a remainder of 4. So I can do that. So that puts a 1. That puts a 1 in the 64 column. Okay. But then I have this remainder of 4. So now what I'm going to do is I'm going to take 4 minus 32. 4 minus 32. Now, if I do that, it's going to give me a negative again. Okay? So I can't do that. Okay. All right, so that gives me a negative. So the 32 gets a 0. Okay. So the 32 slot gets a 0. Then I've still got 4 left here, so I'm going to look at the 16. So I'm going to take 4 minus 16. Okay? And again, that's going to give me a negative. Okay? So let's try the next one. 4 minus 8. Again, that gives me a negative. Okay? So what happens is, what that means is, the 16, it gets a 0. The 8 gets a 0. Now I'm going to do 4 minus 4. So if we look at the next column, we're going to have 4 minus 4. 4 minus 4 gives me a 0. 0. So I can do that, and I end up with 0. So I don't have a negative as a remainder there, or a fraction as a remainder. So that's valid. So what that means is that I put a 1 in the 4's column. So I put a 1 in the 4's column. And now I've got nothing left. Okay, so if you take 0, so if we take 0 and subtract the next column from it, 0 minus 2, well, of course, that's going to be a negative. Okay, or if we look at the last column, 0 minus 1, that's also going to be a negative. All right, so anytime we have a negative, these ones don't work, and so we put zeros in for those. So if we put zeros here, and we put zeros in here. All right, and so the number 324 base 10, so this number here, 324 base 10, is equal to supposed to be my equal sign here, is equal to the number 101,000,100 base 2, or binary. Okay, so these two values are equal. Okay, we have 324 base 10, or decimal, is equal to 101,000,100 base 2. Okay, so these are two numbers that reflect the same amount. Okay, so the amount is like 324, but when I describe 324 in binary, I end up with 101,000,100. Okay, so that is the binary value representing 324 items. Okay, and so the way we calculate this is I think to convert from decimal to binary, I think this is the easiest way. There's other ways that you can do this, but I think this is the easiest way, unless of course you have a calculator. But what you basically do is you take this number and then you subtract it from your binary value. Okay, so you look at these columns in the binary, and so you look at it. So we took 324 minus 256. Okay, could we do that and still have either a positive value or 0? And the answer was yes. Okay, so we subtracted that, and that gave us a remainder of 68. Okay, then we take and we subtracted 128 from our remainder of 68, and we found out that we couldn't do that, right? 68 minus 128 gave us a negative. So that put a 0 in the 128 column. Then we look at the next, which is 64. So then we took 68, which was our remainder still, but we subtracted 64, and that worked. We got a positive out of that, and that gave us a remainder of 4. Okay, so that we put a 1 in the 64's column, and then we had a remainder of 4. So we tried to subtract 32 from 4, and that started giving us a negative. We tried to subtract 16 from 4, and it was still negative. We subtracted 8 from 4, and it was negative. So those all got zeros. Then we subtracted 4 from 4, and that gave us a 0, which is allowed. We're allowed 0. Okay, as long as it's positive. And that gave us a 1 in the 4's column. And then we have a 0 and a 0 because we had nothing left. So we basically just, the rest of them just end up being zeros. All right, so that's how we can convert from the decimal numbering system into the binary numbering system. If we wanted to go the other way, let's forget that we know that the number is 324, okay? But we have this binary value number here, 10100100100, right? This is our binary value, and we want to convert this back to decimal. Well, how do we do that? What we do is we're going to come along here, and we are going to multiply these values. So we're going to take 1 times 256, okay, 1 times 64, and 1 times 4, and then we're going to take the others. We'll take 0 times 128, 0 times 32, 0 times 16, 0 times 8, 0 times 2, 0 times 1, and we're going to add them all together. Okay, but since they're zeros, those ones really don't add, right? So we end up having 1 times 256 plus 1 times 64 plus 1 times 4. And then, like I say, technically what we're doing, though, is we're still adding. We're adding 0 times 128 plus 0 times 32 plus 0 times 16 plus 0 times 8. I'm just kind of spelling it out here so you can see we are doing that, but of course that's all 0. Plus 0 times 2 plus 0 times 1. All right, so we're going to take all this and add this all up. Okay, but of course this is all just 0 here. Okay, so that's just all big 0. So we're really just adding. We're really just adding the values that have 1s associated with them. So we're adding 256 plus 64 plus an extra 4 And that should give us then 324 base 10. Put an equal sign here. Okay, so that's how we can convert back from decimal or from binary back to decimal. All right, so these conversions work really, really well. Make it very easy to do this even when you don't have a calculator at hand. All right, so are there any questions there? Anybody have any questions with how to convert between from decimal to binary or binary to decimal? Okay. Now, of course, I mean, you're going to be doing your homeworks and exams and stuff are going to be online. So, thanks, Drake. So you can use a calculator to do the conversion. That's fine. Okay. But you can do this with any numbering system. Okay. It doesn't just have to be binary or to decimal or decimal to binary. You can pick any base for a numbering system. So I actually had a fellow student who was planning on like trying to build a computer that could read 3 different voltages and therefore use base 3. Okay, and so he wanted to build a computer using base 3 instead of binary, base 2. And the numbering systems will work. It doesn't matter. You could use any numbering system you want. You could also use this numbering system for hexadecimal or octal. However, this is the key point. The reason we choose let me flip over here to the octal numbering system. Okay, the reason we choose the octal numbering system here it is. So the reason we choose the octal numbering system is because it's a one-to-one match. It's a one-to-one match with 3 bits. I need another paint window here. All right, so if you take octal, okay, the octal numbering system means that you use symbols 0 through 7. Okay, so you use symbols 0 through 7, which means that you have a one-to-one relationship with 3 binary bits. Okay, and so you can separate a value into octal by using 3 bits. So if we go back to the one we just did here, which was, we know this is 324. This is 324 in decimal, and it's 101000100 in binary. All right. But if we want to convert that to octal, we simply match up 3 bits at a time. Okay, so we're going to match up 3 bits at a time. So let me paste this over here as a reference. All right, so here we have 100. Those are the first 3 bits. So when you do this, you need to be careful here when you do this, and you need to do it starting from the right-hand side. So you grab these 3 bits, and that gives you 100. And then you find that match, and that's the number 4. Okay, so 100 is the number 4 in either hexadecimal or octal. So right now, technically, we're talking about octal right here. It says hex there because the first 7 are exactly the same. Okay, but at this point, we're really talking about octal here. Okay, but again, the key point of octal is the octal numbering system has a direct relationship with 3 bits in binary. Okay. And so when you start doing this, you need to start from the right hand side and start matching bits. All right, so for this, the first number here in octal is a 4. Let me clear this out of here. All right, so the first number here is a 4 in octal. And then we're going to take the next 3 bits. So we're going to take the next 3 bits and we're going to match those, and that's just, of course, 0. So that's just a 0. And then we're going to match the next 3 bits. So we're going to match the next 3 bits here. 1, 0, 1, which is a 5. So that's the number 5. Okay. And so in octal then, we have 504 base 8, right? So 504 base 8 is equal to 324 base 10, or 101,000,100 base 2. Okay. So the reason we like octal is because it has a one-to-one relationship with binary. So it has a one-to-one relationship with 3 bits inside the binary numbering system. And yet it's easier to say. It's easier to say 504 base 8 than to say 101,000,100 base 2. Right? That's just really clumsy to say it in binary. And not only is it clumsy to say in binary, but it's very difficult to read or to write down or whatever when it's in binary. So it's very hard for humans to see and read binary numbers because we're only talking 324 here, and we already got 9 bits, 9 ones and zeros in the binary. All right, so it's just when you get up to 1,000, you're up to like 10 bits. When you get up to 2,000, you're up to 11 bits. And so you get all these ones and zeros and your eyes just start going crossed. Okay. So it's just very much easier for humans to deal with more than just binary. Okay, even though, remember, the PLC can really do nothing but binary. All right, so, but that's how we can convert to octal from binary. So I recommend that when you're converting between binary to octal or whatever, I don't recommend going directly from octal to decimal or from decimal to octave. I don't recommend that you do that, because the whole point of octal and hexadecimal, which I'll do here in a minute, but the whole point of those is the fact that this numbering system is a one-to-one with binary. So if you're going to convert decimal to binary, and then from binary you can go to octal or hexadecimal if you're going to do hexadecimal, or vice versa. If you're doing octal or hexadecimal and you want to go to decimal, I would first go to binary, because it's so easy to do that. All right, so let me just kind of clean this off here. All right, so now if we wanted then to go to hexadecimal, okay, that I could say the first 7 of hexadecimal is identical to octal, okay, only you don't use the last bits. But in hexadecimal, you have to use the 4 bits, because hexadecimal has a one-to-one relationship with 4 bits in binary. So let me talk about, I keep using the word bit. I don't think I defined a bit. A bit is a single digit in binary. It's either a 1 or a 0. So a single digit in binary, okay, a single digit in binary here is either a 0 or a 1. That's a single bit. Okay. Now, if you take 4 bits, or 4 bits, that gives you okay, so 4 bits gives you what's sometimes referred to as a nibble. Okay. So 4 bits is referred to as a nibble, which is 1 digit in hexadecimal. All right, so a hexadecimal, with hexadecimal you have 4 bits gives you one exact digit in hex. And so that's why we like to use hexadecimal, just very similar to the octal. All right, now if you take 8 bits, that gives you a byte. Okay, so 8 bits gives you a byte. And I'm sure you've heard the term byte a lot, right? When you go out and you buy memory for a computer, you buy something like 256 megabytes, or 3 gigabytes. Okay, so a byte represents 8 bits, and when we talk about memory inside of any digital computer, we usually refer to it in terms of a byte. But 8 bits is 1 byte, so that means you have 8 ones and zeros in a group together. All right, if you take 16 bits, that gives you what we refer to as a word. So 16 bits gives you a word. And 32 bits gives you what's referred to as a double word. And 64 bits, would give you like a quad word. Sometimes though, because most modern computers are either 32-bit or 64-bit, sometimes they may just call it a ward. Okay, but technically 32 bits is a double ward. All right, so if we then look at this, these are our 16 possibilities. Here's our 16 possibilities for hexadecimal. Okay, so again, when you're doing hexadecimal now, you're grouping 4 bits. So we're going to come over here, we're going to group 4 bits. So 4 bits, and you match it 0, 1, 0, 0, which is the number 4. All right. So that is the number 4. And then you have 4 more bits. Grab a different color here. So we're going to have 4 more bits. So you group 4 more bits. Okay, and that's a 0, 1, 0, 0 also. So that gives you the number 4. And then we still have a bit left over here. So what we have to do here is basically add 3 more. Okay, so we're going to just kind of come in here and add 3 more zeros to the left of that. Don't really have room for that, but 3 more zeros to the left. So that gives me 4 more bits, and those 4 bits then match the hexadecimal value of a 1. Okay, so that gives me the hex value of a 1. So when we look at this, okay, and hex, the number 144 base 16. So the number 144 base 16 is equal to 324 in decimal, or 1010010 in binary, or 504 in base 8. All right, so all of these 4 values here represent the exact decimal value of 324. They're simply representing them in a different numbering system. All right, so that's how we can convert between either octal to binary, or this one here is showing hexadecimal to binary. So you're grouping, for hexadecimal, you're grouping 4 bits for one of those 16 unique values, which are 0 through 7, okay, or 8 and 9, and then A through F. So that's how we convert through the binary systems. Now, a lot of these slides in here are just kind of giving you different examples on how to convert between the various numbering systems. Okay. This right here is showing you a timer. I actually have one of these in my office. This is a timer that is a binary-based timer. So what it does is it's got these little, what they call dip switches. These little switches A lot of times you'll find on a circuit board or something, and it's an on-off type switch, but it uses binary. So the first bit would give you like 1 second if you turned it on. The second bit would give you 2 seconds, and so on. So here's just trying to show you the dip switches. And so if you look at this, the red dots indicate that those switches are turned on. And so you can see which ones are turned on here. And then you can calculate how long does this timer take to expire. And so you add these values up to get that. So if we look at like ladder logic, you could kind of see here we would actually have an enabling switch to enable the timer, and then based on what these seconds are, and then you would wire this into your relay to start a motor or whatever it is that you want to turn on. So this would be kind of how we would wire this thing up into some ladder logic. So when you flip the switch on, the timer would start timing, and then after the time has expired, it would go into 0. But the counting of this is done in binary. All right, so like I say, a lot of these slides are just kind of walking you through different methods of trying to do the conversions in that. All right, so let's talk a little bit about this binary coded decimal. Okay. So binary coded decimal uses decimal, which means it's only going to use 10 values, not hexadecimal, which uses A, B, C, D, E, and F. All right. And so there's actually a lot of displays, a lot of mechanical kind of displays that have been created and sometimes are still in use that uses this binary coded decimal. And so binary coded decimal, it needs 4 bits, but it doesn't use those last 6 bits A through F. Okay, so it only uses values 0 through 9, but it requires 4 bits to encode that, and that's why they call it binary coded decimal. It's truly not a separate numbering system. It's just a representation of decimal values using 4 bits inside the computer. Okay. All right, another encoding is called ASCII. ASCII stands for American System, American Standard for Information Interchange. And so code, American Standard Code, lost the C there, sorry, American Standard Code for Information Interchange. And so when we talk about, if we wanted to send the letter A from one computer to another computer, or the letter Q, or a question mark, all right? Again, the computer can't handle anything but 1s and 0s. So anything other than 1s and 0s has to be encoded. And so the ASCII chart shown here is an encoding of letters and digits and semicolons and equal signs and periods and question marks and all the different types of things that we use in normal ordinary text, that if we want to send it, like I say, from one computer to another, we have to encode it, because again, the computers can't do anything but 1s and 0s. And so this is the ASCII chart was the original encoding. Now the original ASCII chart was only 7 bits. And the reason for that was because in the early days when we would be trying to send this information from a computer to the next, communications was not very reliable. And so what they would do is they would use the 8th bit as what they called a parity bit. And so you could have either even parity or odd parity. So if we take like the letter A I've got underlined here, right? That is 7 bits, so it's 1, 0, 0, and then 0, 0, 0, 1. Okay. And so what it would do is you look there and there's 2 1s. So if you were doing even parity, it would count up how many 1s you have, which is 2, which is an even number. And so it would send the parity bit as a 0. And then you would send it down to the other computer, and the other computer would count how many 1s you have. And the key was that the other computer had to know you were doing even parity. And so it would add up the number of 1s, and if the number of 1s matched, then it would say, oh, I'm happy. And so, you told me that you're sending me an even number of 1s, and I got an even number of 1s, I'm happy. Okay. But on the other hand, if you were sending it odd parity, and with the letter A only has 2 1s, and so the parity bit, it would set as a 1, so that when it got down to the other end, it would say, hey, look, I got 2 1s, and then I get the parity bit as a 1. That's an odd number. I was expecting an odd number of 1s. I'm happy. All right? And so you could actually set up the computer to send 7 bits, and then the parity bit is even an odd parity or even parity, and it was your choice. But the key was that both computers had to understand that, yes, you're doing even parity or odd parity. All right? And that, again, that was a check. So if you were sending it the letter A and it received 2 1s, but you were told that you were doing odd parity, then what would happen is the guy who received that would come back and say, hey, I'm confused. I only got 2 1s. I got an even number of 1s, not an odd number of 1s. Send it again. So it was like an error correction that they would send. However, as time went by, our communications got better, and they decided they didn't need the parity bit anymore. And they started sending, they still send something similar to the parity, but they send now they send like 64 bytes, and then they send a sum in there. It's called a cyclic redundancy check, CRC code. And they would send that code that would tell it how many 1s it was expecting. And again, if it doesn't get it, then they ask for it to be resent. But so what they did then was they extended the ASCII chart. So they came up with an extended one, which used 8 bits. Now this ASCII chart, it only has the standard A through Z. But notice here, it's got A through Z in capital letters. And then it's kind of cut off here, I see now. But it's also got over here at 61 is A through Z in lowercase letters. Okay, and I guess the actual letter got cut off on this slide, but notice that a capital A and a lowercase a are different, and so you have to encode that differently. All right, and so that pretty much used up all 128 possibilities in 7 bits. But then when the communication started getting better, they're like, you know what, we can extend this to 8 bits and send more information. So the 8-bit extended ASCII code includes things like some Greek letters and some other European letters that you might see in text. And so then they're like, well, that's all fine and dandy, but what about the rest of the world with like Chinese characters and Japanese characters and Russian characters and Arabic characters, and what about the rest of the world? Because remember, ASCII stood for American, so this was a code created here in the United States, and it handled the English language, but it didn't handle any of the other languages. And so they came up with what they call Unicode. So now you hear the term Unicode. And so Unicode is 16 bits. With 16 bits, it gives you 16 bits gives you 65,000 possibilities. Okay, so you have 65,000 possible letters or symbols that you can send using the Unicode. But the first 256 is identical to the extended ASCII code. All right, so let me check, see if there's any questions here. Anybody putting any questions in chat? No? All right, so I'm going to move on then. All right, so let's talk about how do you add numbers. So if we take the numbers 5 plus 5, okay, in decimal, if we try to add this in decimal, 5 plus 5, now remember in decimal, okay, so in decimal numbers here, we only have the possible values of, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, so when we're talking about the decimal numbering system, these digits are the only valid digits we can use. So if you tried to add the number 5 in decimal to the number 5, you end up with a value of 10, but you can't use that. So that's where we come up with the tens column, right? So you end up saying, well, this is 1 times 10 plus 0. Okay. So when you do binary in base 2, you have to do the same thing. So you have to do this carry bit. However, what happens when you try to do subtraction? Okay, so if you had, let's say you had the number 10 in binary. So if we have the number 10 here in binary, and we're going to try to subtract 5 from that, right? Then we can borrow, right? We would say we're going to borrow from the tens column to subtract, because we have 0. We're in the ones column, we're doing 0 minus 5, which we can't do. So we would borrow from the ones column, or from the tens column, so that we could do the subtraction and get a 5. So if we're doing that in binary, well, that might work okay. However, if we're trying to build a computer, remember, a computer is electrical circuits. And to try to build a circuit to do this borrowing thing is very, very complicated. It really gets complicated really, really quick. So what they've come up with is something they call the complement. Right? So instead of building a computer circuit that will subtract, they've learned that, you know what, if we store, so let's say I want to subtract minus 5. We've learned that if we store the number as a negative 5, and then we can simply add them. All right, so we can, instead of subtracting 5 from 10, we can take minus 5, right? If we negate the 5, we can take minus 5 and add it to 10, and that would give us the same value, right? So they came up with this idea that we're going to do a ones complement, okay? And then we're going to do a twos complement. Now, ones complement just takes all the ones and makes them zeros, and all the zeros and makes them 1. And that's a ones complement, but when you try to do that, the circuitry still gets complicated. But what they've found out, who I'm not sure who we give credit for on this, but somebody figured out that if we do a twos complement, we can simply add 2 binary numbers and ignore any carry, and we're done. All right, so when you look at -5 in binary. Okay, so -5 in binary, okay, is going to be the number 5. Okay, so the number 5 out to 4 bits is 0101. All right, we already saw that before when we were doing our conversion. So the number 5 is 0101. All right, so if we're talking about a +5, we're gonna add one more bit here, which is we're gonna call the sign bit. So this is the sign bit. All right, so this bit right here is going to be the sign bit. So the leftmost bit is the sign bit. And if it's a positive, we're going to make it a 1. All right, so, or excuse me, if it's positive, we're going to make it a 0. Sorry, I said that wrong. So the sign bit is the leftmost bit of a number. And so that's going to store that, and a 0 indicates it's a positive number. So then if we want to make it negative, what we do is we take the complement. So to make it a negative, we take this 5-digit number here. So we're going to take this 5 number, and we're going to convert take this 5-digit number. And what we're going to do here is we're going to convert each one of these bits from a 0 to a 1 or 1 to a 0. So if the bit is a 0, we're going to make it a 1. And if the bit is a 1, we're going to make it a 0. All right, and that gives us the 1's complement. So if we have the 1's complement, if we simply add one more to it, so if we add 1 to the 1's complement, that gives us the 2's complement. So you see here, here's the 1's complement. 11010 is the 1's complement of a +5. And we add one more to that, so that gives us 11011. That is the 5, that is a -5. So this value right here is -5 stored inside the computer as a 2's complement. All right. Now, it's really easy to build circuitry that can flip a high to a 0. As a matter of fact, it only takes a single transistor inside of an electrical circuit to convert a low voltage to a high or a high voltage to a low. Right? It's a simple transistor. You put the 0 into the base of the transistor, and the output is automatically inverted. All right, so technically it only takes like one transistor to convert a high to a low or a low to a high, so we can flip or do the 1's complement in very, very simple circuitry inside of a computer. All right, and then we can use an adder circuit to add one more to that. All right, and then so if we take the number 10, so the number 10, +10 down here, this is a +10, which is 0 for the sign, positive sign. And then 1010 is 10. And then this is -5. So we're going to add +10 and -5. And that gives us this 5-digit number here, this 5-digit number, which is 00101, which is a +5, and we're going to ignore the carry. This 1 is a carry. We're just going to ignore it. Forget about it. Okay? So we end up with our number, and it's a positive 5. So we know that plus 10, right? So this number here is a plus 10, and this number here is a minus 5. All right? And so that has this, there's a carry, and then we're left with positive 5. So we wipe out this carry, we just ignore this carry, and we get a positive 5. So 2's complement. 2's complement is how we deal with subtracting numbers. And again, the reason for that is because if we tried to build a subtraction circuit, we would have to worry about borrowing from the next higher column within the number. And that circuitry, to build that electronic circuitry inside of a computer, is just a nightmare. But if you instead, to do subtraction, you take the number, you do a 2's complement on the number, and then you can simply add it. And addition circuits are actually really easy to build. And complement circuits are really easy to build. And so that's why when we store a number as a negative number inside of a computer, or we try to do subtraction, we take the 2's complement of that. So we negate the number by complementing the number and then adding 1 to it. And that makes it the 2's complement. So the 2's complement for a negative number is going to look like this. Now, in the homework, I might ask you, what's the 2's complement of a positive number? It's just the number, right? So here is the number 5. Inside the computer is the positive 5 inside the computer as a 2's complement. It's just the number. All right, so I'm pretty sure I have a question about that. So if it's a positive number, it's just that number. But if it's a negative number, we take the 2's complement. So you take the positive value, you flip all the 1's to 0's and 0's to 1's, and then you add 1 more to it, and that gives you the 2's complement for that gives you the negative value.